Scientific Methods Conceptual Framework. At the onset of this project, a conceptual framework was developed to consider how the global airline transportation network may act as a conduit for the importation of dangerous infectious diseases into Canada. The framework contemplates a series of three interconnected frontiers where Canadian efforts may be directed to minimize the likelihood of importation. See Exhibit 1. The first frontier considers the emergence of infectious disease threats from an international source. Threats may arise secondary to 1. Naturally occurring phenomena such as those driving the recurrences of influenza pandemics, and 2. Breaches at laboratories harboring dangerous pathogens, and or 3. The intentional release of infectious agents as acts of bioterrorism. The probability of achieving source control at this frontier is a composite of factors including but not limited to 1. Characteristics of the infectious agent causing the threat and the setting in which it arises. 2. Promptness with which the source location recognizes, identifies, and characterizes the threat. And 3. Rapidity, intensity, and effectiveness with which the source location responds to the threat. The second frontier considers the transportation of infectious agents via the global airline transportation network. In this report, only infectious agents that can be carried by passengers and generously as a latent infection or active disease or exogenously on articles of clothing or formatives are considered. While most endogenously transported agents cause a human disease and consequently have implications to public health, exogenous transported agents may be the source of plant or animal infections that carry only economic consequences, e.g., hoof and mouth disease virus and the cattle industry. Infectious agents may be transported directly from source to destination via non-stop flights or indirectly via connecting airports. Opportunities to detect and respond to threats exist at airports where passengers embark, connect, if applicable, and or disembark. The third frontier considers the entries of infectious agents via commercial airports into their final domestic destination within Canada. The probability of preventing threats from entering the general population is dependent upon the point of entry's ability to 1. Quickly recognize, identify, and characterize the threat, and 2. Rapidly and effectively respond to it. Should an infectious agent pass through the point of entry undetected, then its final domestic destination could be potentially become a secondary source of disease exportation. In public health terms, preparedness and response efforts directed at the international frontier are considered akin to primary prevention strategies since they aim to prevent the entry of infectious threats into Canada altogether. Efforts directed at the transportation network frontier are considered akin to secondary prevention strategies since they aim to detect and control threats en route to Canada before they interacted with the general population. Finally, efforts directed at the domestic frontier are considered akin to tertiary prevention strategies since they aim to minimize the health and or economic consequences of infectious disease threats once they have already breached Canada's borders. Data contents. Data used to conduct the scientific research to produce this report are organized into two categories. A. Commercial air travel includes information about the global airline transportation network and its role as a conduit for the international spread of infectious diseases. Data are global in scope but have been analyzed with emphasis on determining how Canada and its major regions and cities are interconnected with the international community. The primary sources of commercial air traffic data used in this report include the Official Airline Guide (OAG), Airports Council International (ACI), International Civil Aviation Organization (ICAO), International Air Transport Association (IATA), Worldwide OAG. The official airline guide data from 2008 were used to study the architecture of the global airline transportation network, shedding light on how cities and countries around the world are interconnected. These data were also used to determine the types of flights entering cities, i.e., domestic or international or both, as well as the degrees of separation between cities, measured in flight connections needed to travel between a given city pair. All measures of centrality, i.e., degree betweenness, closeness, were all calculated using 2008 worldwide OAG data. ACI data were analyzed across a period of 96 consecutive months between January 2000 and December 2007. This analysis facilitated the careful study of seasonal patterns and evolving long-term trends in domestic and international passenger traffic across Canada's major municipalities. Due to the intrinsic nature of ACI data, all passenger flows are measured in arrivals plus departures. ICAO data were analyzed across 28 consecutive quarters between the beginning of 2000 and the end of 2006. This analysis was conducted to compare and contrast the flows of international passenger arrivals between the northern and southern hemispheres and different regions of the world. Furthermore, ICAO data were used to analyze the proportion of international traffic arriving into Canada's major municipalities from US and non-US points of origin over time. Worldwide IATA data from 2007 were used to study passenger flows between city pairs around the world. It bears noting that these flow data represent the true flight origins and destinations of passengers, as they take into account the specific routes and the connection points, if applicable, used by travelers. IATA data were used for a number of purposes, including 1. Producing heat maps that depict the flight origins of international passengers traveling into Canada. 2. Ascending the actual routes used by passengers traveling between cities around the world. 3. Conducting mathematical simulations of the worldwide spread of influenza. B. Global conditions. The importation of infectious disease threats into Canada are a composite of three conditional probabilities. 1. The probability of disease emergence at a given source location. 2. The probability that the source location detects and controls the threat before it accesses the global airline transportation network. And 3. The probability that international air traffic leaving the source location directs the threat into Canada's borders. 10 variables have been selected as surrogate markers for the emergence of infectious disease threats, with the emphasis on pandemic influenza and the abilities of countries to detect and control infectious disease threats at their source. These data are presented to complement the commercial air traffic data in this report and to help readers better assess the overall risk of global infectious disease threats to Canada. Variable 1. Global human population density. In km square grids, data on global human population density were obtained from the Socio-Economic Data and Applications Center (SEDAC) at Columbia University for the year 2005. Density values are presented worldwide in 1 square kilometer grids. This level of resolution addresses an important limitation of density data presented at the national level, which averages population values over densely and scarcely inhabited land areas. Variable 2. Global poultry population density in km square grids. Data on poultry populations worldwide were obtained from the Food and Agriculture Organization (FAO) of the United Nations for the year 2007. Concerns about avian influenza and its potential role in the emergence of a new pandemic strain of human influenza led to the inclusion of this variable. Poultry density is also presented worldwide in 1 square kilometer grids. Variable 3. Global human poultry population co-density in km square grids. This co-density index was calculated as the product of human and poultry densities for each square kilometer grid worldwide. Areas with the highest co-density were considered optimal grounds for the interaction of avian and human influenza viruses and consequently for the emergence of a pandemic influenza. Variable 4. Highly pathogenic H5N1 avian influenza in humans. Data on cases of highly pathogenic H5N1 avian influenza in humans were obtained from the World Health Organization (WHO). Countries with the highest numbers of human cases were considered high-risk area for the emergence of a pandemic influenza. The cumulative number of human cases between January 1st, 2003 and December 31st, 2008 are presented in a choropleth map. Variable 5. Cities with operation laboratories reported to hold WHO risk group for microorganisms. Data on the coordinates of laboratories is reported to hold highly dangerous infectious pathogens were obtained from open sources, although these laboratories tended to be highly secured. There are precedents of accidental breaches which could trigger international outbreaks. The locations of the world's known laboratories holding WHO risk group 4 microorganisms are presented as points on a world map. Variable 6. National economic status data on gross national income per capita were obtained from the World Bank as an index of poverty, with the data reported by countries between the year 2000 and 2006. Countries with extensive poverty were those potentially facing conditions that could contribute to the emergence of dangerous infectious diseases, e.g., extensive crowding, inadequate sanitation infrastructure, etc. Variable 7. National health expenditures per capita. Data on national health expenditures per capita were obtained from the World Bank for the year 2005. Countries with limited healthcare resources were considered those potentially facing difficulties rapidly detecting and characterizing emerging infectious disease threats. Variable 8. National physician density data on the number of physicians per capita were obtained from the World Bank and the World Health Organization. Given the wide time frame in which data were reported, national values are presented in a choropleth map with 3 color ramps. Each ramp represents a specific time period with the greatest degree of confidence in the most current data, i.e. blue ramp 2005 to 2008, and the weakest degree of confidence in the most outdated data, i.e. green ramp 1990s to 2000. And countries with a few physicians per capita were considered likely to face challenges detecting and responding to emerging infectious disease threats. Variable 9. National nurse density data on the number of nurses per capita were obtained from the World Bank for the years 2000 to 2004. Countries with a few nurses per capita were considered likely to face challenges detecting and responding to emerging infectious disease threats. Variable 10. National hospital bed density data on the number of hospital beds per capita were obtained from the World Bank and the World Health Organization. Given the wide time frame in which data were reported, National values are presented in a choropleth map with two color ramps. Each ramp represents a specific time period with the greatest degree of confidence in the most current data, i.e. blue ramp 2005 to 2007, and the weakest degree of confidence in the most outdated data, i.e. green ramp 2000 to 2004. Countries with a few hospital beds per capita were considered likely to face challenges responding to emerging infectious disease threats requiring hospitalization. Data quality. The commercial air traffic data used to produce this report were obtained from major international organizations, each of which has procedures in place to ensure data quality. However, our scientific team developed a set of secondary procedures to ensure that all commercial air traffic data were rigorously assessed before any analysis was initiated. The steps involved in this data quality check are described below. First, all three-letter IATA airport codes from each of the four commercial air traffic data sets, i.e. OAG, ACI, ICAO, IATA, were matched and compared to verify that each code represented a unique commercial airport. Subsequently, a city master file was created that aggregated airport data for cities with more than one commercial airport. For all variables with continuous values, a series of descriptive statistical analyses were performed to identify missing data elements and to detect the presence of outliers. Subsequently, the flows of air traffic in cities were plotted across time to facilitate a visual assessment of patterns and consequently identify unexpected deviations. Finally, autoregressive time series models were developed to generate best fits with observed city-level flows of air traffic. Residuals from these models were then plotted, with explanations sought for large discrepancies, i.e. where observed values exceeded 2 standard deviations from expected values. Where unexplained discrepancies existed, queries were made back to the original source. Data analysis. Geographic units. Cities represented the primary unit of analysis in this report. In most instances, airport level and city level analysis are synonymous with the exception of cities with multiple commercial airports. For such cities, data from each commercial airport were aggregated into a single unit representing their collective characteristics. For global subgroup analysis, the world was divided into 10 distinct regions as indicated below and shown in Exhibit 2. The list of countries included in each world region was adapted from definitions used by the United Nations. The regions include 1. North America, 2. Mexico, Central America, and the Caribbean islands, 3. South America, 4. Western, Northern, and Southern Europe, 5. North Africa and West Asia, 6. Sub-Saharan Africa, 7. Eastern Europe and Central Asia, 8. East Asia, 9. Southern Asia, 10. Australia, New Zealand, and Pacific Islands. Certain subgroup analyses were performed that distinguished the developing from industrialized regions of the world. The developing world was defined by excluding 1. Northern America, 2. Western, Northern, and Southern Europe, and 3. Australia, New Zealand, and Pacific Islands from the 10 regions listed above. Furthermore, a number of analyses considered the global airline transportation network from the perspective of a borderless European Union (EU). At the time of this analysis, the EU comprised 27 members. States include Austria, Belgium, Bulgaria, Cyprus, Czech Republic, Denmark, Estonia, Finland, France, Germany, Greece, Hungary, Ireland, Italy, Latvia, Lithuania, Luxembourg, Malta, and the Netherlands, Poland, Portugal, Romania, Slovakia, Slovenia, Spain, Sweden, and the United Kingdom. For Canadian subgroup analysis, Canada was divided into 7 distinct regions as depicted below and shown in Exhibit 3. Additionally, 6 major Canadian municipalities were selected for subgroup analysis as they represent the locations of the country's quarantine stations. The 7 regions include 1. Ontario, including Toronto and Ottawa; 2. British Columbia, including Vancouver; 3. Quebec, including Montreal; 4. Alberta, including Calgary; 5. Atlantic Canada, including Halifax; 6. Saskatchewan and Manitoba; 7. Northern Canada. With 10 world regions, 7 Canadian regions, and 6 Canadian municipalities, 130 potential subgroup analyses are possible. In this report, the intersection of global and Canadian regions is examined as deemed necessary. Statistical analysis. Descriptive statistics were used to analyze the passenger flow volumes, identify the routes and transit points used most frequently by passengers en route to Canada from around the world, and examine trends in passenger traffic over time. All statistical analyses were conducted using SAS version 9.1. Network analysis. The architecture of the global airline transportation network was analyzed using network analysis. All analyses were performed using 2008 data from the Official Airline Guide (OAG). In 2008, there were a total of 3,445 cities with commercial airports in operation worldwide. All network analyses were performed using this number of cities. Examining the airline transportation network from a global perspective, a connectivity matrix was produced to visually depict the words commercial aviation arteries. The connectivity matrix comprises 2 axes, along each of which 3,445 cities with at least 1 operational commercial airport are represented. Each of the 35,122 dots on the matrix represents the existence of an artery directly connecting a city pair, i.e., arteries represent non-stop flight routes connecting city pairs. For definition purposes, non-stop flights are considered those where the aircraft does not land anywhere between the departure city and the destination city. By comparison, direct flights are considered those where the aircraft does land somewhere en route to the final destination city. At this location, new or onboard passengers may or may not be permitted to embark or disembark the aircraft respectively. Throughout this report, cities are considered directly connected only if there is a non-stop flight between them. Cities within Canada were evaluated to identify the types of flights that they are capable of receiving. For Canadian cities, the categories included those receiving 1. Domestic flights only, 2. U.S. international flights, in addition to domestic flights, and 3. Non-U.S. international flights, in addition to U.S. international flights and domestic flights. The use of the word international in airport names was not considered, as some airports do not currently accept international flights but have in the past, and have kept the term international in their name. Conversely, other airports do not use the term international but clearly receive international flights. Analysis measuring degrees of separation between world regions and Canadian regions and/or municipalities were also included. In network theory, directly connected nodes generally have a greater potential for flow relative to nodes that are not directly connected. With increasing steps between nodes, the potential for flow diminishes. In the context of infectious disease threats, this implies that cities connected through non-stop flights are most vulnerable to the exchange of infectious diseases between them, with risks of spread decreasing with increasing steps. Network analysis was also used to generate three established measures of centrality: in degree, betweenness, and closeness. In the case of this report, in degree centrality communicates vulnerability to infectious disease threats since it identifies the number of non-stop pathways into a city from elsewhere in the airline transportation network. Conversely, out-degree centrality communicates the potential risk that a city will export an infectious disease threat. For the purposes of this analysis, only in-degree centrality is reported. To assist with the interpretation, total or global in-degree centrality values for Canadian cities are divided into three categories: 1. Domestic, and 2. US, and 3. Non-US international. The values for each category represent the number of non-stop connections into a given city from domestic, US, and non-US international points of origin. This analytic approach enables readers to evaluate both the number and type of inbound pathways into Canadian cities. International in-degree values for many European cities are somewhat artificially inflated, given that flights between different countries of the European Union (EU) are defined as international, even though the EU is, for all practical purposes, a borderless entity. For specific analysis of international in-degree centrality, the EU has been defined as borderless, providing a more reasonable assessment of the significance of European and non-European cities worldwide. Between centrality is a measure of how frequently a city lies along the shortest path between other city pairs through the global airline transportation network. Cities with a high betweenness have the potential to be important locations where diseases pass through, since travelers generally prefer to take the shortest route to their final destination. Heightening infectious disease surveillance in the airports of cities with high betweenness may be a strategy to consider if intercepting the movements of infectious agents within the global airline transportation network is under consideration. In networks, nodes with a high betweenness tend to be very important with respect to their ability to facilitate or restrict flows. In this analysis, betweenness values for all cities were normalized between 0, lowest betweenness, and 1, highest betweenness. It bears noting that a city's betweenness centrality is a structural metric that reflects their potential as a conduit for passengers to travel through while en route to their final destination. Under real-world circumstances, passengers for a variety of reasons may not actually use the shortest paths available. In a separate set of analysis, cities with the highest betweenness centrality values worldwide and cities that are passed through most often as transit points worldwide are compared. Closeness centrality is a measure of how accessible a given city is to all other cities in the global airline transportation network. For this analysis, closeness has been calculated taking into account the travel time for each passenger seat to move between every city pair worldwide. To calculate the travel time for passenger seats, closeness values were weighted by aircraft size, i.e. the number of passenger seats for each type of aircraft and the traveling speed of those aircraft measured as median flight times between city pairs. In the context of infectious disease threats, cities with high closeness centrality are at greater potential risk of importing infectious disease threats than cities with lower closeness centrality values. As with betweenness, closeness values were normalized between 0, lowest closeness, and 1, highest closeness. All network analyses were performed using Project version 1.23. Mathematical analysis overview 1 overview. An mathematical framework was employed to integrate the science of infectious diseases with network analysis and transportation geography. Through this convergence of scientific disciplines, the spread of diseases within and between the world cities is examined. Simulations are used to determine if and how diseases are likely to penetrate Canada's borders through commercial air travel. Given present-day concerns about highly pathogenic H5N1 avian influenza and its potential role in triggering the next influenza pandemic, simulations throughout this report have been developed based upon the biological characteristics of the seasonal influenza virus. All simulations have been conducted using 2007 worldwide passenger traffic data. These data reflected the actual movements of passengers throughout the global airline transportation network by accounting for connecting flights and the actual flight paths used by passengers. The infectious seed used to initiate each simulation entails the introduction of 2 infectious and 10 exposed individuals at each hypothetical disease epicenter. For each simulation, it is assumed that there are no effective measures in place to prohibit infectious persons from traveling via commercial aircraft. 2 types of simulations are performed. First, outbound simulations are those in which a single city is selected as a hypothetical disease epicenter and the outward spread of disease is subsequently observed. Inbound simulations are those in which 596 global cities outside of disease is substantially observed. 2 United States, and 3 Western, Northern, and Southern Europe, i.e. cities with the highest international air traffic volumes, are selected as a hypothetical disease epicenters, and the outward spread of disease is subsequently observed from each city. An analysis is then performed to determine which epicenters most frequently result in the exportation of a disease into Canada. While outbound simulations evaluate threats based on specific what-if scenarios, inbound simulations identify which cities in the world would pose the greatest risk to Canada if they were the source of an infectious disease threat. To illustrate how importation risks to Canada vary across seasons, inbound simulations are conducted for each quarter of the year. 2. Dynamical systems. Dynamical systems are distinguished as either deterministic or stochastic. Deterministic systems are ones which exhibited identical behavior when analyzed repeatedly using the same initial set of conditions and parameter values. Conversely, stochastic systems involve randomness and consequently exhibited variable behavior when analyzed using the same set of initial conditions and parameter values. As such, deterministic systems provide insights into average behavior, while stochastic systems consider the distribution of possible realizations stemming from a single event. Given the intrinsic randomness with which infectious diseases spread from person to person and city to city, stochastic simulations have been used throughout this report. To evaluate the effects of a stochastic stochasticity. 5,000 simulations were performed for all outbound analysis. For inbound analysis, 2,000 simulations were performed for each of the 596 hypothetical disease epicenters considered. 3. Spread of infectious diseases between cities. A metapopulation framework was used to simulate the spread of infectious diseases between cities around the world. Conceptually, metapopulations represent a network of populations that are interconnected with one another. The theoretical framework for this interconnectivity is rooted in graph theory, where each network node, i.e. population, is part of a multi-digraph, i.e. a directed graph in which the arcs joining nodes are oriented in a specific direction. An important limitation of the kind of a metapopulation framework used in this report is that it assumes a homogeneous mixing of individuals and consequently infectious diseases within cities. 4. Spread of infectious diseases within cities. An SEIR model was developed to simulate the person-to-person spread of infectious diseases within the world cities. SEIR models consider individuals in one of four epidemiological classes. 1. Susceptible. 2. Exposed. 3. Infectious. And 4. Removed. Susceptible individuals may become exposed and infected during contact with an infectious person. Thereafter, infected individuals remain asymptomatic during the infectious agent's incubation period, i.e. the time between exposure and the development of illness. Subsequently, individuals may become infectious. After remaining infectious for a period of time, individuals may then either recover with the immunity or die and thus are removed from the infectious class. To simplify the SEIR model, a number of assumptions are made. 1. The total population of a given city is assumed to be effectively equivalent to the number of susceptible individuals in the population. This is because the model focuses on newly emerging infectious diseases for which it is assumed that individuals lack intrinsic immunity. 2. The number of removed individuals is negligible over the short, i.e. 21-day time horizon used for simulations. These two assumptions mathematically simplify the model to focus on two epidemiological classes: exposed and infectious. The stochastic EI model used in this report is a continuous time, discrete space Markov chain. A general overview of the model is described below. 1. The system at time 0 is the state x of t0. This state indicates the number of exposed and infectious individuals at time t0 for every city throughout the global airline transportation network. 2. Based on the state x of t0, the time at which the system makes a transition is determined. This time is a randomly quantity determined by a random variable with an exponential distribution. 3. When a transition occurs, the nature of the transition is determined. Potential transition possibilities including the following. A. In a city with infectious individuals, an uninfected individual may become exposed, leading to the development of a new latent infection. B. In a city with exposed individuals, an exposed individual may become infectious. C. In a city with infectious individuals, an infectious individual is removed from the infectious population due to the recovery with the immunity or death. D. An exposed individual in city A travels to city B. E. An infectious individual in city A travels to city B. The relative probabilities of these outcomes are determined using information about the biological characteristics of the infectious agent of interest, i.e., seasonal influenza, in this report, and worldwide passenger traffic flows via the global airline transportation network. For the process repeats itself from step 1. All mathematical analyses were conducted using MATLAB version 7.7. Detailed information about the mathematical models used in this analysis is presented in the technical appendix. Cartography. All maps were carefully designed with respect to color and drawing elements for optimal viewing on flat screen liquid crystal display (LCD) or cathode ray tube (CRT) monitor. Maps are well suited for color printing but are not designed for black and white printing or photocopying. To provide readers with the fullest geographic detail possible while maintaining sound cartographic design, a number of maps have been hyperlinked to a GIS server. Maps available for viewing via the server utilize scale-based rendering, which provide readers with added layers of geographic detail as they are needed. Readers may also freely interact with the maps and their data elements via the GIS server, or cartographic work in this report was conducted using Environmental Systems Research Institute, i.e. ESRI, ArcGIS 9.3 software. Several different types of maps are presented throughout this report, each of which varies in its depictive purpose. These maps are described below to assist with the cartographic interpretation. Maps presented in this report generally fall into one of 4 varieties. 1. Network architecture. 2. Passenger flows. 3. Disease emergence and control indicators. 4. Simulations. Network architecture maps are designed to illustrate structural features of the global airline transportation network. Examples of architecture maps including those demonstrating Canadian and US cities by the origin of flights received and the number of flight connections required to enter a particular region. In Canada, from around the world, passenger flow maps are predominantly presented as heat maps, i.e. they use color differences to depict variances in flow volumes. These maps are designed to describe the spatially discrete quantitative differences through space in a narrative visualization that treats them as continuous wave-like spatial fluctuations. It should be stressed that these maps are not, strictly speaking, spatially precise. Rather, they are abstract visualizations designed to direct the eyes of readers to cities in the world where passengers are initiating trips to Canada in their greatest numbers. The presence of a hotspot illustrating high passenger volume at a particular city may extend some distance beyond the city's borders and potentially coalesce with other hotspots from neighboring cities. Readers should also be aware that colors depicting passenger volumes are shown on land masses only. Consequently, small islands or cities directly adjacent to major bodies of water may have smaller hotspots than cities surrounded by larger areas of land. When interpreting heat maps, readers should initially inspect the volume of passenger arrivals bar to assess the maximum flow of passengers represented by the map's hottest areas. Each heat map is unique in this regard, depicting relative flows of passengers. Consequently, different heat maps should not be compared directly to one another, but rather interpreted independently. Disease emergence and control indicator maps have been produced to describe Area level factors such as the magnitude of human cases of avian influenza, a country's overall economic status, or the quantity of health and human resources available. Most are produced as choropleth maps using solid color differences to depict the differences in values at a national level. Others, however, such as those depicting human or poultry populations, use varying color saturations throughout pixels of spatially gridded data to visualize differences in density in square kilometric units. Simulation maps use graduated symbols to illustrate the probability of infectious disease importation to a given city. Two types of simulation maps are shown. One, outbound simulations use orange graduated symbols, while two, inbound simulations use red graduated symbols. A description of each type of simulations is provided in the mathematical analysis section of the scientific methods.